Let's imagine we took a stone and threw it into a pond. You get a little ripple effect going like this in some direction. And we'll call this direction c, that would be the speed of light or the direction of light. And we'll say it's in the x direction. So this is going in the x direction there, forward. Now you can also imagine a little boat here, and that boat would just be shifted side to side in the waves. So it'll be going maybe in the y direction here. So we'll label this the electric field portion of the electromagnetic waves. This is going in the y direction. So we say EY, and that's the boat. And over here, I'll put a little B, and the B is flying with the water. So it's just going up and down. It's not going to move left or right. It's just going to move up and down with the waves. So it's just moving in the z direction. So we'll call this the B, and that's in the z direction. And we can also notice a couple of things. So we can say that the electric field is going to be perpendicular to the magnetic field. And this is going along the y-axis, and this is going along the z-axis. Well, if that was going along the x-axis. This orientation is going to be consistent, so you'd have to remember that. And we could also notice that EY crossed with BZ would give us the C in the x. So if this is the x direction, then we're going to have the E field going in the y. And we're just going to make one period right here, like that. And we'll notice that the E max would be over here. But we can also try to draw now the magnetic field, so that will just be going in the z direction. And you'll see that it would be going almost exactly in the same way that the E would be going, as you can see. So it reaches the top just when that reaches the maximum, and it reaches the minimum just when that reaches the minimum as well. So we'll be able to put the B maximum here, and this would sort of correspond to this point. And this would be the end of our wavelength right here. So the reason it kind of looks like this is because we have these equations. We have E in the y direction is equal to the E max times sine of kx minus wt. And we have for the bz, that's just going to be B max times sine of kx minus wt. And so they have the same equation, and so therefore they would have the same shape, both like they're in phase. This is one of the main points. They're in phase. Not only that, but they cannot exist independently. And they have the exact same equation here. So they're going to reach the maximums at the same point, just in different dimensions, I suppose. And over here, they're going to reach the same minimum point in different dimensions. So from here, we'll get a couple more expressions. We'll be able to say that the speed of light here is equal to the electric field divided by the magnetic field, which is equal to the frequency times the wavelength, which is equal to 1 divided by the square root of mu naught times epsilon naught, which is equal to W divided by K. This is what we're getting here now. And this is called the angular frequency, of course. And this is the wave number. Wave number. What the hell is that? Well, let's not get too carried away here. Let's say that omega, W, is equal to 2 pi times the speed of light divided by lambda, the wavelength. And then we'll see that K is equal to 2 pi divided by the wavelength. And what this is trying to say is, if you have a high K, you'll have a lot of wavelengths in a certain distance. And if you have a low K, well then you'll have less wavelengths in that same distance. It's going to be less frequency. Now this equation, the frequency times the wavelength, is very interesting because it's telling us that the number of oscillations per second, the number of oscillations per second times, and that's the frequency, times the wavelength, and that's the wavelength, which means how long it is. This must be equal to 3e to the 8 meters per second, which is the speed of light. And that means that we're going to get this spectrum of light waves, which would be Roy G. Biv. Roy G. Biv. This is the colors because, well, it's not always going to go with the same oscillations. So you're going to have different wavelengths and stuff that you have to sort of match, and everything has to be that same speed, which is crazy. And we also should know that a light year is equal to 9.46 e to the 15 meters. So this is crazy. So if we were to try to imagine what this really looks like, let's say this is one photon right here, and then this beam is simply a stream of photons. And so when the photon is at different points along this x-axis, it'll have different field strengths. And if we were to try to quantify the energy of one single photon, then that would be equal to Planck's constant times the frequency. And that's what you'd have to sort of look over here for that. But Planck's constant is going to be equal to 6.626 e to the negative 34. And this is in joules divided by hertz. So you'll see that if you just multiply the frequency by that number, you'll get the energy. This is Planck's constant. So here we were finding the energy of a single photon, which is like finding the charge of a single proton. But if you were trying to find the energy of a beam of photons, that would be like finding the current. And so now we're going to label this Poynting vector, which is kind of like the rate of energy flow. And so we would say S is equal to 1 over mu naught, and then we'd cross E with B, and that's how you would get energy over time, and then you could divide that by the area. And this is an instantaneous value. Well, because E and B both have sign values, we have to use the root mean squared in order to figure out what their averages are. But first, let's figure out what the S max would be. That's just going to be equal to E max squared divided by the speed of light times mu naught. And then we'll be able to define I as intensity. And that's just going to be equal to the average, or the magnitude of the average of this vector. And this is called intensity. So we also say that I is equal to the ERMS squared divided by C mu naught. So you can see we're just taking the average there. And this would give us a power source divided by 4 pi d squared. Let's say we had a photon. It would emit light in all directions, so you'd have to find the area of that sphere. It's the surface area of the sphere here. Now you'd have the power divided by the area, right? And so that would be watts divided by meters squared. And this is an average value for the Poynting vector, the intensity. Now if you're hit with a beam of light, you're going to experience some radiation. So we'll define P rad as equal to the intensity divided by the speed of light. Now we'll also be experiencing a force, so the radiation force is going to be equal to the intensity times the area divided by the speed of light. Okay? And so you'll notice that the P rad is simply the force divided by the area, and this would be newtons divided by meters squared. Now there are two ideal scenarios for the radiation pressure. One when it's totally absorbed, and one when it's totally reflected. Now both of these expressions are going to be for total absorption. total absorbed. And this one as well, total absorbed. However, if you want to get the total reflected, then you need to multiply these by 2. So multiply by 2 to get the total reflection. And here you could also multiply this by 2 to get the total reflection. Okay, now normally it would be somewhere in between this, but like these are idealized scenarios for what we do in our math. Now usually light is unpolarized, which means that the oscillations here, they kind of go off in completely random directions. Usually we would represent that with just like the arrows going in all 4 directions like this. So you get like the plus E's over here or over here, and then the minus E's over here or over here. But in reality, this would really just be going in all directions, and you would never really be able to predict over time where those oscillations would sort of point. This is an unpolarized light. Now let's say that light starts bouncing into things and it starts becoming polarized. What that means is that these materials will only allow a certain component of the electric field to go by. So let's say normally you get the electric field in this direction. So this would be the positive E and this would be the negative E's. As you can see, they're going to have positives and negatives. But this particular material is only going to let by the EY. So you'll only get the Y components. And you won't get any X components. Now, you'll notice that there's a little angle that we're making here with the polarization like structure here with the material. So depending on which direction that you're polarizing in and which direction your E is pointing, you're gonna get this little angle, and that angle is the polarization angle. Polarization angle. So you could also get the negative E component here, EY, this would be negative. But you can see we didn't get any X component, we just got the Y component through this polar structure. So we have 2 scenarios we need to remember. If the initial light wave was unpolarized, then you'll want to use the equation IF equals 1/2 I naught. And you can also call this the 1/2 rule. You'll just get half the intensity on the other side. But if the I naught was already polar, then you should use IF equals I naught times cosine squared theta. Okay, now light can also be reflected and refracted. So if this was the water right here and this was the air, then light could come down from here and hit the water, be reflected at the same exact angle here, and be refracted at some other angle. This is refracted and this is reflected. So this angle is just going to be, we'll call it theta 2, and over here we're going to get theta 1 on both sides. Now there's this thing called the index of refraction, which we'll denotate as n, which is simply the ratio between the speed of light in a vacuum divided by the velocity of that beam of light inside of the medium that they're in. And so this is the index of refraction. So as an example of the index of refraction, let's say air or a vacuum, the n will be equal to 1, but in the water, n is equal to 1.33. And we also have this little relationship that says n2 sine theta 2 is equal to n1 sine theta 1. Well, with this expression, we're able to say that if n1 equals n2, then theta 1 equals theta 2, and so we'll get no direction change. But if n1 is less than n2, then theta 1 will be greater than theta 2, and therefore this will be refracted toward the normal. And this would be the normal here, or here on the bottom side. You could see it be refracted towards the normal there. And if n1 is greater than n2, then theta 2 will be less than theta 1, and this will be refracted away from the normal. Now, a pretty crazy phenomenon is this thing called total internal reflection. Let's say we had 4 light beams here. This one is just going to shine up here, and it's going to go straight up. This one is going to shine here and get refracted a little bit over here. This one is going to shine here and get refracted even more. And this one is going to be at a perfect angle that the entire thing will be reflected inside. And this is called the critical angle. So we'll define the theta c being equal to the arc sine of n2 divided by n1. And this is the critical angle. Let's discuss another important angle called the Brewster angle, and we can really also call this polarization by reflection. Polarization by reflection. Because all the light that's reflected is going to be 100% polar. So let's say we had our light coming through here, and it's going to come off at the same angle here, of course. But it's also going to be refracted down here. And what's curious to note is that you'll have both components of the magnetic field, and that'll be coming through here. The magnetic field is simply just going to be preserved. But the electric field, when we go through here, we'll start with the electric field going this way, maybe going that way, this way, that way. But then over here, we're going to lose the electric field, and over here, it's going to maintain. So we again get that one there, here, here, and here. So you can see how this is only a partially polarized light beam because we still have both components, although they might be smaller. Here you might get bigger components, right? But over here, you lost the electric field. That is only the magnetic field at that point. So we have a few equations that we can state here. So if these are the 2 Brewster angles that we'll label as theta b, so this is the 2 Brewster angles, theta b, then we could say, and maybe this one is the refraction angle, theta r. Let's make the expression that theta r plus theta b equals 90 degrees. And then for theta b, we can simply state that theta b equals arctan of n2 divided by n1. So theta b, the Brewster angle, equals arctan n2 over n1. And just a reminder, this one is fully polar, whereas this is partial polar, the one that's refracted. So actually, this is how you can get complete total polarization by reflection there. Interesting.